Okay, folks, we are ready to continue with Chapter 8. And Chapter 8 is about this concept of confidence intervals, and we've actually kind of addressed this already in talking about standard error and the idea that there's a range plus or minus when we use a sample to estimate a population parameter, like a population mean. We know that there's a range plus or minus where that sample mean is likely to fall, and we know that that sample mean is also normally distributed, so we can calculate that range with a certain probability level, 90%, 95%, 99%. So we've actually kind of already done this, so I just have to introduce one little adjustment that we need to make based on an issue with small sample sizes, and that's called the t-distribution.
I ain't going to no airport, Hannibal. I ain't gonna fly with that crazy fool Murdoch. If he's flying, then we're dying.
No, not the Mr. T distribution, just T distribution. Now, don't be alarmed about learning a whole new distribution, because it's very similar to this normal distribution, and the way we do all the calculations will be pretty much identical. And actually, Excel will do all that work for us once we get the hang of it. Then we'll just talk a little bit about how confidence intervals work, and then we'll get right into the homework problems. Remember, last time what we did was inferred population parameters such as mu, the population mean, used with a point estimate based on the random sample. And we can say we trust that estimate due to the fact that the sampling distribution of the sample mean, x bar, is itself normally distributed with its own mean mu and standard deviation sigma over square root of n. We don't have sigma here, typically. That's the population standard deviation. So what we've been doing is just saying, well, we've got a sample, we've got a standard deviation of the point estimate of the x bar, and that's probably close enough to approximate the sigma, so we just use s over square root of n to come up with our standard error. However, when we use this s instead of the sigma, we're actually losing normality in the sampling distribution of x. And it's not going to be an issue unless we've got a pretty small sample size, but sometimes we will have small sample sizes. So that's really what we're thinking about here. We have to make this adjustment with small sample sizes. And so we can't be confident that we have a perfectly normal distribution. We have to make an adjustment, and that adjustment is known as a t-distribution. Okay, and here's what you need to know about the t-distribution. It's like a normal distribution, but fatter tail. So if I just drew it over here, let's say this is a normal distribution with mean mu, standard deviation, sigma, and everything we know and love about the normal distribution. 68% of our observations within plus or minus 1 sigma, 95.5% plus or minus 2 sigma, etc., etc. Okay, so that would be a normal distribution. Now, our t-distribution is going to look exactly the same. It's going to be a bell curve, but it might have a lower peak and fatter tail. So what we'll say is there's going to be more observations out in the tails, and the shape of that will vary depending on what's called the degrees of freedom, which is an adjustment factor that depends on the sample size. And the degrees of freedom is set to n minus 1, so we take the sample size minus 1. And if that's small, so you have a small sample size, you have small degrees of freedom. So for instance, if n equals 10, if we only sample 10 items, and our DOF is n minus 1, which is 9. So our parameter will be 9 degrees of freedom. That'll be a really fat tail distribution with many more observations out here in the tails and not as many in the middle. Okay, but if as that n gets larger, so as n gets larger, like 20 degrees of freedom, n minus 1 is 19, our t-distribution will start looking more and more like a normal distribution. Okay, now, to use the t-distribution, we're going to jump into Excel here and practice having Excel do this calculation for us here in just a second. But we've got to find t-values. Now, what is a t-value? Well, a t-value is the equivalent of a z-value. So when we're working with normal distribution, if we knew all the population parameters, we could convert any point on that distribution into a z-score by taking value minus the mean divided by the standard deviation. And the z distribution is just the normal distribution with mean 0 and standard deviation 1. Okay, well, we kind of have the same concept with our estimates of our population parameters, and we could normalize them by saying z equals x bar. That's the point estimate, that's the sample mean, minus mu, over. Now we have to use a concept of standard error when we are dealing with sample mean, sigma over square root of n. And we could take the same concept with respect to our sample means. We could standardize them. Now the problem is we're not working with normal distributions with small sample sizes, we're working with t-distributions. Okay, so instead of calculating z-scores, we're going to calculate t-scores. But it's going to be exactly the same procedure. T is defined as x bar minus mu over s over square root of n. So we don't have sigma, remember, so we're using S, which is the sample standard error, as our population standard error estimator. When we're dealing with small sample sizes, we're going to, in setting up confidence intervals, which is what we're getting ready to do here ultimately, we're working with t-scores instead of z-scores, and this is what we need to calculate t-scores, and then that'll kind of tell us in terms of the t-distribution how many standardized I should say how many normalized standard deviations we are away from the mean. Now, what does this have to do with confidence intervals? We'll want to be able to say something like, can we be 90% confident that our sample mean x bar is capturing the true population mean? Because that x bar is normally distributed, remember, or maybe t distributed if we have a small sample size. What we'll want to do is say, what's the 90% probability area on either side of this distribution? And then using that standardized t distribution, we won't calculate sigmas, we'll calculate t-scores. And then we'll have something both which we can kind of tack on to our sample mean. So let's say the sample mean is measured sample mean is 10.1. Well, we'll use and we have a small sample size, so we'll use a t-distribution to calculate, using everything else, our values for t, and let's say the value for t is plus and minus 0.8, so we'll be able to say we're 90% confident that the true, let's see, t equals 0.8, so it's plus or minus. So we'll say, well, we're 90% confident that the true population mean is within 9.3, is between 9.3 and 10.9. And that right there is called our confidence interval. We'll come back to that here in a minute. I'll talk about that a bit more just to make sure we know what we're doing. But first, let's jump in and do some practice. And we're going to practice problem 8.1. The book says calculate the following probabilities using Excel. This is problem 8.1 if you want to follow along, page 341. Probability, let me write these down. Okay, so first it says probability T10, that's the degrees of freedom right there. So a t-distribution with 10 degrees of freedom is greater than or equal to 1.75. And it just says where T10 has a t-distribution with 10 degrees of freedom. Okay, so how do we solve that? Notice we've got a t-dist. Okay. Returns a left-tailed student's t-distribution, two-tailed student's t-distribution, right-tailed student's t-distribution. And then the inverse, just like we did with norm inverse. So if we're given a probability, we can use inverse to find the scores. If we're given a score, we can use t-dist to find the probability. Now, the only question is, do we want to do left-tailed, two-tailed, or right-tailed? Well, let's think about what those mean for a second, and then I'll show you. Okay, so here's our t-distribution, and it's saying, we've got the mean of the distribution plus and minus 1 sigma. Basically what it's saying is, what's the probability area in this t-distribution with 10 degrees of freedom that's greater than or equal to a t-score of 1.75. So that's way out here to the right of 1 sigma. We're saying greater than or equal to that, so we're only looking for this area under the curve. Well, so what is that? That's right tail, right? So we want a one-tailed t-score, and we want the right tail. In fact, let's do t-distribution, t.dist dot rt, and then the x, that's the value 1.75, and then the degrees of freedom, that's 10. Okay, and so what it says 0.05, 5.5%. We can in fact display that as a percent. Okay, 5.5% of the distribution is out here to the right of 1.75 sigmas, 1.75 standard deviations from the mean in that particular t-distribution. Now, remember, every t-distribution has a slightly different shape depending on the degrees of freedom parameter. Okay, but that's pretty easy, right? So let's do a few more of these. There's 5 total. Let's just do them all just to get familiar with the concept of the t-distribution and using it. But you'll notice it's very familiar, I hope, to what we've done related to the standard normal distribution in z-scores. Okay, so B says PT degrees of freedom 100 is greater than or equal to 1.75. Now, what's the distribution going to look like with that many degrees of freedom? That means n is 101. Well, it's going to look much more like the standard normal. And so what's the area under that going to be? It's going to be a lot less. And let's verify that by setting it up here. Equals t dot dist dot right x 1.75 degrees of freedom 100. Okay, so we're looking for a number much closer to 0. And indeed, it's 0.04. Not a whole lot closer, but it's substantially smaller. Okay, it's about 20% smaller. So that verifies what we thought, what we expect to see based on the definition of the t-distribution. Okay, so let's keep moving on. C says P Z. They're going to throw something at us now. They want us to go back and do a z-score. Probability Z is greater than or equal to 1.75. Standard normal, where Z is a standard normal random variable. Well, the only reason they're asking us to do this is because they want us to compare that result to what's obtained in A and B, and then explain the difference in these probabilities. Okay, well, remember, as we get more degrees of freedom, we approach a normal distribution. So this is going to be an even thinner tail out here above 1.75 in z-score terms, and so we expect a number even smaller. Okay, and in doing this, I have to remember that when I have a normal distribution and I've got a z-score out here of 1.75, actually what we were used to was having something that we know was normally distributed, but not having it standardized yet in z-score terms. So I would have, like this would be my 10 point, this would be my 10.1, and the mean, let's say, is 8.5, and the sigma is 3. So I plug those values in, and then get the probability to the left, or the area under the curve to the left of this value. I'm looking for it for the right of the value. I don't have a norm.dist.rt function, so what I have to do is 1 minus the norm.dist for Excel to report the area to this side of that value. So as long as I know that, I can run with this. So what I'm going to do, I'm going to do 1 minus parentheses norm.dist parenthesis, the x is 1.75. Now, what's my mean here? I'm already in a standard normal, so my mean is 0. Standard deviation is 1, right? And then true for the cumulative probability, double parentheses, 0.04. And what did I say? I said I expected that was lower, and it is. It's just a little bit, though. Just a little bit smaller than the 100 degrees of freedom. Okay, so as we've mentioned, as your degrees of freedom gets larger, your t approaches your z. Your student's t-distribution approaches your fully normal distribution. All right, a couple more here. Let's see what else we got. D says the probability, let me draw this. D is the probability of a t 20 degrees of freedom being less than or equal to minus 0.80. Okay, and this will be a breeze, or just wanting us to get used to the idea of using the t-distribution left tail, and that we don't need to add anything. Notice it says left-tailed right here. So t-distribution, the x is minus 0.80. The degrees of freedom is 20, and the cumulative is true. Okay, we've got 21%, 21.6%. I like to go ahead and convert these to percent because that's what it's really given us. Remember, that's what the P is for, probability. Okay, now finally E. E says P T with 3 degrees of freedom. Whoa, that's a small sample. Less than or equal to minus 0.8. So that equals t dot dist. X is minus 0.8. And degrees of freedom is only 3. Cumulative true. 24%. Okay, and then it says, how do you explain the difference between this result and the result obtained in part D? Well, it's because the degrees of freedom smaller. That's what it's all about. Okay, so we only have 3 degrees of freedom here. We have a much fatter distribution that looks more like this. Whereas if we have 20 degrees of freedom, it looks more like this. And if we have 100 degrees of freedom, it's almost exactly the same as the normal, so it looks like that. Okay, so here, this is our 100 degrees of freedom, our 20 degrees of freedom, our 3 degrees of freedom. That's what's going on. So we squash down the distribution, we put more of the events out into the tails, because we just have more variability with smaller sample sizes, as you hopefully remember from the last homework. Okay, and that's why we have to make use of this concept of the t distribution. Okay, so we know how to use it now, though. I hope it's very familiar, and we know that calculating the t-scores is analogous directly to the z-scores. So let's move on, talk a little bit more about confidence intervals, and then we can do the rest of the Chapter 8 problems. So we know we need to use a t-distribution in t-scores instead of the z-scores in the standard normal for small sample sizes. Now we can address this question: how confident are we in the accuracy of our sample base point estimate of, and we're going to stick with population means, so mu. So this is where the confidence interval comes into play. Now here's the textbook definition. Confidence interval: an interval that, with a stated level of confidence in terms of probability, percent, so we'll say something like 90%, captures a population parameter. So for my example I was using above, if our sample mean, x bar, is 10.1, we want to be 90% confident that, or we can say we're 90% confident that the true value of the population mean is between 9.3 and 10.9. And how do we say that? Well, just remember, because our t value, our t-score, was plus or minus 0.8. So we took the 10.1 and we added the 0.8, and that gives us the 10.9. That's our upper bound of our confidence interval, and then we subtracted the 0.8, which gave us a 9.3, the lower bound. And so we're going to say 90% of the time from sampling, this range is going to capture that true population parameter. Right? Now, what if we want to be 95% confident? What's going to happen to the interval? 95% of the time, it's going to be within this little bit broader range. 99% of the time, it's going to be even a little bit broader range. And we don't necessarily want a larger confidence interval. What if we want a smaller confidence interval and 95% certainty that we've captured the population parameter? Well, in that case, we're going to have to use a smaller sample size. As we use smaller and smaller sample sizes, our confidence interval will shrink down. So if we go from sample size 10 to sample size 100, we might get something like this. You know, we might be dealing with something like 9.8 and 10.4. That leads us to these two rules that we need to understand about confidence intervals. For higher confidence or probability levels, the intervals are wider. We want to think about that in terms of just the area under the curve. And let's say this is a t-distribution. And let's say it's a pretty small degrees of freedom. So here's our mean of our t-distribution and our plus and minus sigma. Now, if this was a standard normal, how much percent of the outcomes would be within plus and minus 1 sigma? 68%. But a t-distribution has fatter tails, so it's going to be smaller than that. It might be only 60% of the observations show up in that range, leaving more of them to be out in the tails. We're saying if we want to be more certain that this captures the true value, we widen the tail out, and now we might, if we add another 15% on each side, now we're at 90. We want to go to 95. I want to add another 2.5% on each side. I need to widen out my interval. Okay, now I'm at 95. And we can set the confidence interval wherever we want. We can set it at 96, 98, 99. If I go to 99, I'm going to have to go way out here, and let's see, add another 2% to each side. And another 2%. Okay, so wider intervals gives us a higher p-value and a greater certainty that our estimated parameter lies within that range of the true population parameter. Okay, the only other rule we need to know is that for larger sample size n, the intervals are smaller. Two ways to think about that. One is that with larger sample sizes, our t-distribution approaches a normal distribution. So here's a t-distribution for, let's say, n equals 3. And then for n equals 20. And then finally, n equals 30. It starts looking a lot more like a normal distribution. Okay, so in that n equals 3, this range here, let me just pick a range, left to right. In the n equals 3, that might have only captured, something like 70%. But in my n equals 30, which looks more like a normal, I'm capturing, maybe like 90%. Okay, so sample size goes up, we get closer to a normal distribution, and the normal distribution is a skinnier distribution. Okay, the other way to think about that is if you just think about the definition for confidence interval, the formula is x bar plus or minus the t-value at the specified confidence level times the standard error of x. Okay. Well, remember, standard error of x is defined by sigma over the square root of n. Okay. What happens to this value as n gets larger? Okay. Well, as n gets larger, square root of n gets larger, so we're dividing s by a larger and larger number. That means s is becoming smaller and smaller. So as n increases, this right here gets smaller. So we're multiplying the t-value by a smaller number. So we're going to be at that, the whole thing here is going to be smaller. This whole thing gets smaller. And so we're adding and subtracting a smaller range from our sample mean. Okay, so larger n, here's what happens to our confidence interval. Our 90% confidence interval might look like this when n is 10. But if we go to n equals 100, our 90% confidence interval now looks like this. Okay. So the lessons are we can have a better chance of capturing the true population parameter with either a larger n or a wider confidence interval. If we knocked it down to 80%, it'd be a much better chance we captured it. The typical one we're going to that you'll see in a lot of statistics and science and even business applications is the 95% confidence interval. And we're pretty familiar with that from the normal distribution already, the standard normal. That's roughly plus and minus 1 sigma. It's a little bit, I'm sorry, that's roughly plus and minus 2 sigma. It's actually a little bit more than 2 sigma, but approximately 2 sigma. Gets you pretty close to 95%. In our t-distribution, of course, it's all going to depend on the degrees of freedom. We'll start working with those concepts here in the problem set. Okay, so let's jump into 8.5. Here we've got the salary data on all NFL players in each of the years 02 to 09. And I think we're only going to look at the year 09. We're not going to do this for every year. It says, because this file contains all players for each of these years, you can calculate the population mean for each year if population is defined as all NFL players that year. However, proceed as in the previous chapter to select a random sample of size 50 from the 2009 population. That's what we've got here in the 2009 data. Based on this random sample, calculate a 95% confidence interval for the mean NFL total salary in 2009. Does it contain the population mean? Okay, so first, let's calculate the population mean first off, and we only want total salary. So you know what? I'm just going to go ahead and get rid of a lot of other stuff here. I only want total salary, and let's calculate population mean. That's the average, the whole thing, and wow, there's 1,830 players in there. Pretty impressive. I've got 1.867 million. Okay, that's just kind of a benchmark. We'll come back to that. Now we're going to generate a sample. And actually, I'm going to copy this and paste its value just so I don't lose it if I screw something up. Okay, to get a random sample, I need random numbers. Equals rand. Fill those down. Let's give it some more decimal points. Okay. Now, I need to remember fix my random numbers by pasting the values. I need to fix this label. I'm going to call this fixed random numbers. There we go. Now I can sort on my fixed random numbers. Sort by fixed random numbers, smallest to largest. That's fine. Okay, now pick the first 50, which is going to be 2 through 51, and that's going to be my salary values I pick. So I'll just go ahead and grab the salary values. Control C, and I'm going to paste that over here. And that is my n equals 50 sample of salaries. Now let's calculate our sample mean. Okay, my sample mean equals average of H2 to H. Okay, and I'm at 1.97 million instead of 1.86 million. Right? Because of the randomness in the sample, we're either going to overshoot or undershoot a little bit, but we're going to get it pretty close. And remember what we did in Chapter 7. If we take a whole bunch of samples, we'll see that the more samples we take, we'll be there 9 times out of 10. We'll be pretty close to the population parameter. Well, that's what we mean by a 90% confidence interval. Or we'll be there if the sample gets bigger, that sample mean gets closer to the population mean. So we can either take more samples or take larger samples, and then we can dial this in and get a better and better chance of capturing the true population mean. Okay, and the only other thing it wants us to do here is it says calculate a 95% confidence interval for the NFL, for the mean NFL total salary in 09. Okay, we got to get back to that confidence interval formula. Let me write this down for us. Confidence interval, and that is plus or minus the t value times standard error of x. And the book calls it a t multiple. T multiple times the standard error of x. Okay, so a t multiple. Okay, to find that t multiple, previously in 8.1, what we did was find the probability of a given outcome, knowing the t-score. Now we know the probability, and we want to find the t-score, the t-multiple. So we're going to use the t-inverse function here. And the t-inverse function is very simple to use. We'll just do t.inv. And we want to do two tail, by the way, because we're finding the probability in the middle. We're cutting off either tail. 2t. The probability is 0.95, and the degrees of freedom is n minus 1. Our n is 1830, so 1829. Okay, so we've got 0.0627. Let's take some decimal points off of that. As our t multiple, and now we just need to calculate the standard error of x, and then we can multiply it times the t multiple, add and subtract it to our sample mean, and we'll come up with our range for our confidence interval. Okay, so I've done my t multiple. I've done my t multiple. Now I need to calculate my standard error of x bar. And remember, that is defined as sigma, if we know sigma, over the square root of n, or approximately s, the sample standard deviation over square root of n. And we do know sigma, but I'm going to go ahead because working with the sample and assuming we only have the sample, I calculated the sample standard deviation here, and let's just go ahead and work with it. So standard error equals the sample standard deviation there, F5, divided by square root of my sample size, which was 50. Okay, so my standard error is 409,000, and my confidence interval factor then is that standard error 409,000 times the t multiple 0.06. Confidence, and I'll call this confidence interval plus minus. And so that's just the t multiple times the standard error. And I'm looking at a range of $25,000 plus or minus. And now I'll say my confidence interval range here from the minimum to the maximum. The minimum, of course, is just equal to my sample mean minus the confidence interval value. And the maximum is just equal to my sample mean plus the confidence interval value. Okay, so what I'm saying is that, and let me highlight these two numbers here, because this defines my range of the confidence interval. What I'm saying is that we're 95% confident that, or that we could say a 95% probability that the true population mean lies between these values. Okay, and our sample mean, sure enough, is between those values. The textbook tells us to it says does the confidence interval contain the population mean? And actually no, it doesn't. Our population mean is a little bit below our confidence interval. Okay, folks, I am learning along with you. So I ran this. I did 10 samples, and I wasn't capturing the population mean in my confidence interval but one time. So I've been scratching my head and trying to find out my mistake, and I finally realized it. So if you've been following along, my deep apologies. I'm not going to start over the whole problem, but I'll show you that the mistake is pretty easy to correct. And my mistake, I should have realized it when I looked at my t multiple, is only 0.06. And what I forgot to do was take 1 minus the probability we're trying to capture. So I should actually take 0.05 in that t inverse rather than a 95%. And if I do that, my t multiple is somewhat close to 2, which is about the same as would it be in a normal distribution. And let me just show you the mistake I was making so we can all learn from this. So here's a t distribution, and if I want to capture 95% between these boundaries, I have to exclude 5%. Well, the t dot inverse dot 2t is giving us the t score here, minus t plus t, that cuts off that probability. So if we're trying to capture the middle 95, we're going to cut off the outer 5%. So I need to put the 5% in my t dot inverse calculation, not the 95%. Once I made that simple fix, my confidence intervals, of course, got a lot bigger, and then plus or minus those confidence intervals, yeah, they capture that population mean now 9 out of 10 times. And if I kept doing this, we'd see that that would converge on 95 out of 100 times, and that's what the 95% confidence interval really means. Yeah, I'm saying we're 95% confident that the true population mean lies between these values. That's technically not true. The reality is that if we do this 100 times, this whole exact procedure, 95 times on average, our confidence interval will capture the true population mean. Okay, so that was a little rough, and I apologize for not having that set up exactly right, but you can hopefully follow along and replicate that. And then in problem 8.7, you will get the chance to do a similar problem all by yourself. I will be waiting for questions and comments on email and the discussion forum to help you make it through that.